In this video lecture, we're going to deal with scoping in programming languages and how we can use symbol tables in order to implement scoping rules in programming languages. So far we've looked at different kinds of program errors. So we looked at whether a program is lexically well-formed, whether the identifiers have valid names, or the strings are properly terminated, and whether it has known characters, like there should not be any unknown characters. And these are the lexical errors that we were finding in our lexer. We also looked at errors when we looked at the syntax of a programming language. So when we're parsing it, we want to make sure it's syntactically well-formed, the package declaration has the right structure, expressions are syntactically valid, and so on. There's many, many more syntax errors than there are lexical errors. But let's say that a program is lexically well-formed and syntactically well-formed. Does this mean that the program is legal? We know that this is not the case. Like, there could be programs that are semantically illegal, and we need to make sure that we find those program errors as well. Let's take an example decaf program. It's a fairly simple decaf program, and if you look at the syntax of this decaf program, it is perfectly valid in terms of its syntactic structure. But if you look at it a bit closely, you can see various things wrong with it. You cannot define an array type as a local variable in decaf, and in this program that's happening. So we need to catch this kind of error and report it. There's another error in the same statement where the array size is defined to be of size 0, which again is not allowed in the decaf specification. There's a variable there which is being used, but it wasn't declared anywhere, so we need to catch that. We also have cases where this variable mybin is actually declared, but is declared as a boolean, and it's trying to participate in a multiplication. That's not allowed either. You cannot multiply a boolean value. It's not a valid case of coercion either. Foo is defined twice. It's already been defined over there, and it's defining it again. You cannot redefine the function, so somehow we need to catch that and report it. The use of foo in this expression, it's being added to the result of a function, Fibonacci. Fibonacci returns an integer, but foo returns a void, and you cannot add a void to an integer. It's not allowed. And so this is another semantic error that we need to catch and report. So in all of these cases, we need to know about the identifiers. We need to know what their types are so that we can catch these types of semantic errors. Finally, there is no main function in this program. We need to catch that as well. We need to have some entry point into a decaf program. So what's the goal of semantic analysis? Is very simple. It has to ensure that the program has a well-defined meaning, and we need to verify various properties of the program that are not caught during the earlier phases of lexing and parsing. All the variables should be declared before they get used. All the types should be used correctly in expressions and method calls, etc. Method calls should have the correct number, types of parameters, and the return value should match up. And if you use a method call inside an expression, then you should make sure that the return value is valid for that expression. Various challenges in semantic analysis. We want to be able to reject all or most of incorrect programs. Sometimes it may not be possible for certain programming languages to reject all incorrect programs that are semantically invalid, in which case we want to do the best job we can in the compiler. We definitely do want to accept all correct programs and not raise an error. If there is no semantic error, we should not incorrectly say that there is an error. That would be bad. There's some nuances in semantic analysis. We can get those out of the way so that we know that we're not discussing these cases in the rest of this lecture. There's a conditional here. This conditional always evaluates if statement is never evaluated as true, so it never does a block. So if you look at that assignment of 137 to a string variable x, it's not an error in an interpreted language because it'll never reach there. When it's executing the statements line by line dynamically, you will never get there because the if statement won't let you get there. So it's not an error in an interpreted language. Can be a type error in a compiled language unless you have an optimizer that just removes that statement If you do that before you check for errors, then you won't get an error. However, if you're checking for type errors before you do optimization, you might raise a semantic error, even though the optimizer is going to remove the statement. So this is like a corner case. We are not going to consider in the rest of the lecture, but it's good to keep in mind that this could happen. There's also a nuance of validity versus correctness. So in this example of a function that's supposed to define the Fibonacci series, the return value for n less than or equal to 1 is written as return 0. It's actually incorrect. It should be return n, not return 0, but it's not something that is considered semantically invalid, right? It's just a bug in the program. Obviously, semantic analysis doesn't mean that we're going to find all possible bugs in somebody's code. For one thing, that's going to be way more difficult than doing semantic analysis. And in fact, it's undecidable in the general case. So we can't even do it, even if we wanted to. So there are various challenges in semantic analysis. We want to reject the largest number of incorrect programs. We want to accept all correct programs. We want it to work fast. There are some other goals of semantic analysis. We want to gather some useful information about the program that can help us during code generation. We want to determine what the variables are meant by each identifier. So if there's a variable that's used as a function, we want to make sure that we store all the information about it. We want to build an internal representation. If the programming language has inheritance in object-oriented programming languages have this issue of inheritance hierarchies, and symbol tables are a useful place to store that information. And we'll see an example of this later on. You want to keep track of variables in scope, which are in scope and which are not in scope at each program point, at each point in the program. So scoping is going to be really important. When we implement semantic analysis in an attribute grammar, we're just going to augment the parsing rules to do the checking during parsing. So every time you do a reduce action, you can actually manipulate the symbol table, insert a new symbol table, insert an identifier into the symbol table. If you go out of scope, you remove a symbol table, and so on. Essentially, what this leads to is a single pass semantic analysis. So as you finish parsing, you also finish your semantic analysis. In some other cases, you could, instead of doing it using attribute grammar, you could build the whole abstract syntax tree first, then we use recursion to explore the tree. And sometimes you might do this more than once for multi-pass semantic analysis and code generation. So let's look at the problem of scoping in programming languages. So the first thing is, what does a name signify? So in some programming languages, if you have a name or that you need to keep track of, it depends on whether the name is a function or a type or a variable, and so on. So this code here, as you can see, uses the same identifier A, and is using it as a class variable. It's using it as a type. It's using it as a function name. It's using it as a type here again. And it's got a variable name, which is a parameter, so each of the different uses of the same name is given a different color here. But obviously, Java code doesn't come colored. It's just going to be very confusing to anybody reading it. So nobody wants you to do this, even if it's perfectly legal. You want to keep your identifiers readable and so that a human can understand what's going on in the program. But if you look at the Java specification, it does allow you to do this. So a compiler has to deal with cases like this. In C++, you can also do some awful things. Like you can take a variable which is defined here as X. You can redefine it as a string in a local scope. That's fine. But then in this if statement, inside this conditional, you're allowed to create a new variable X and define it as float X and then give it a value. So this is a new X that's defined inside the conditional part of the if statement. And so when I do this, it's totally valid because it's using the locally defined version of X, the one that was defined here. And I'm creating a new variable double X here. So this is again a new X, and I'm assigning it a value. Perfectly legal, but quite ugly code to read. But again, we as a compiler, C++ compiler has to deal with these cases. You cannot say that this code is ugly, I'm not going to allow it. If it's valid according to the specification, then the compiler has to deal with these cases. So what is scope? The scope of an entity is a set of locations in a program where that entity's name refers to that entity. So you define it somewhere and then you use it in various other places, right? So the introduction of new variables into the scope may hide older variables. So you can use the same name in a new scope, and that might shadow an older definition. So we want to keep track of what's currently visible, and that's a problem of scoping. In order to deal with scope in programming languages, the common way to deal with it is to store that information in a symbol table. And a symbol table is just a mapping from names, which are strings, to descriptors, which is all the information you want to keep about this identifier. So as we run our semantic analysis, we continuously update the symbol table with information about what is in scope, what is out of scope, what is shadowing, which variable is shadowing which other variable, and which, any identifier really, not just variables, but functions as well. So let's take a deep dive into scoping using an example. So here's an example C program with a few printf statements so that we can analyze which variables will be used at each point in this program. So we're going to go line by line through this program and look at how a symbol table, which is just a mapping from identifiers to a descriptor, can be used to keep track of everything. So in this case, what the symbol table we're going to use is a little bit simplified, and the information that we're going to keep in the symbol table is not the values. Well, it can store the values, but what we're interested in is just where the identifier was defined. So in this case, if I look at line 0, I can see that I've defined an identifier X. So in my symbol table that I'm showing you here for this example, I'm storing the identifier and then I'm storing the line number where it was defined. So it was defined on line number 0. So I'm storing 0 into the symbol table here. You could also store the value 137, right? But I'm not going to show that here because that's not that relevant to the example and showing how scoping works. Then we go to the next line, which is line 1. And you can see that we've defined a new identifier and its definition line number is 1. Then we go to the next line. And here we have 2 parameters to the function. So they both get added into symbol table. And the definition line number for them is 2. The next line is something that's going to use the variable. So it has to look up the value of the variables into the symbol table. So that's line 3 here. In line 3, it's going to look up X. It's going to find the nearest X that it can find, which is this one. That's the one defined in line number 2. The Y was defined in line number 2 as well. And you can see the Z, the closest one it can find, is the one that's defined in line number 1. So the symbol table implies you're going to search it from the closest part all the way up to the definitions that you're storing just get added on, sort of like a stack, right? So let's go to the next line, which is 4. There's nothing there. And there's line number 5. We have 2 new variable definitions, X and Z. So notice that this X here is going to mask all of the previous definitions of X. This is a new X that's defined here in line number 5, and that's going to be used locally rather than the ones that are defined non-locally. So that's why scope is keeping track of the scope tells you which definition to use. So let's look at line 6. In this case, you're going to we need a value for Y, because we need for the R value, the right-hand side value of this equation or this assignment, you want the value of Y. So if you look at the symbol table, it's going to be the one defined in line number 2. It's this one over here. And then we're going to assign it to the Z that was defined in line number 5. And then we take the value of Z at line number 5 and assign it to the X, which was defined in line number 5. So that's this one here. And you can see it's all done by searching through the symbol table and finding the first definition that you can find. Let's go to, so that's line 7. Now line 8 introduces a new scope. So there's a curly bracket there that says there's a new scope that's going to be defined inside these curly brackets. So there's inside here is line 9, where it defines a new scope for variable y. It's defined in line 9. And when you go to line 10, you can see there is actually a new scope here. So there would be a new symbol table that gets added, but nothing really gets defined in this scope. So the scope inside line 10 is just using the symbol table and trying to search through it from the closest point up. And so when I look at the X, Y, and Z that I'm using here. Oh, sorry, I forgot the line 9 actually is using X. So this X here is the same one that we saw before. So let's go back to line 10 and look at the first X that we use is again the one that's closest, which is X5. That's the closest X I can find in the symbol table. Y is this one, which is 9, and then Z is 5, which is this one here. Gone all the way up to line 10, and now we are at line 11. Line 11, it's going to take the values of X, Y, and Z. And again, the ones that we can find will be 5, 9, and 5. Those are where those definitions come from. Now we go to line 12, and you can see a scope is ending over there because of the closed curly brackets. So that scope goes away. The definition of Y at line 9 goes away. Then we go to line 13, and now we look for the closest X, Y, and Z. And you can see that the definition here is from line 5, line 2, and line 5 again. Now we go to line 14. In line 14, we see that another scope is going out of scope essentially, so that we are going to get rid of the definitions of X and Z in line 5, because that close bracket is going to finish that block. That scope goes away. And then finally in line 15, the input parameters to the function testfunc also goes away. And now what we're left with are the definitions in line 0 and 1. So as you can see, the symbol table can keep track of this information by taking advantage of this data structure we've seen here. It keeps building the information. As it sees a new scope, it'll create a new entry where there might be a new definition or new for an identifier. So the identifier X can occur multiple times, and then when you use it, you go up this representation and search for the identifier and pick the first one you see, and that's going to be the definition you use. So symbol tables, as we saw, map names to descriptors. And as we run our semantic analysis, we continuously update the symbol table with information about what is in scope and what isn't. And you can see that the implementation is a stack. It's a stack plus search. So you should be able to search through it. You can't only look at the top of the stack. You need to search through the stack. And essentially, each symbol table, we would push a scope. Each scope will have a symbol table of its own, right? You can pop a scope and you discard all the symbol tables that are inside it. You can insert a table into the closest scope symbol table and you can look up a symbol. So these are the basic operations you need if you implement the symbol table using this fairly straightforward method, stack plus search. So when you use a symbol table, you want to exploit the structure of the program. So there might be a block statement, a function call, classes, etc. So whenever you enter a new scope, you want to make sure that you have a new scope where there is a symbol table you can access and put the new identifiers in this new scope into that symbol table. So you're going to add the variable declaration. At this point, you can process the body of a block, a function, or a class, or a package, create a symbol table then. And when you exit the scope, you want to sort of get rid of it. Get rid of everything in that scope. So you want to get rid of the symbol table when you exit the scope. So much of the semantic analysis is defined over the parse tree using symbol tables. Symbol tables are very useful to track all kinds of semantic errors. Let's take a brief look at a slightly different way of implementing a symbol table, which is called a spaghetti stack. So let's take this example here. Let's say that we are in a root scope and we are starting again with sort of line 0, going line by line. When I'm at line 0, again, this here defines a line number, not the value of the variable. So we're just tracking where was this variable defined. Line 1, you define another. And notice that each new one is pointing upwards to its parent. Now we define a function, you get two new definitions of x and y on the same line. We go to line 4, you can see that there is two new variables, w and z, and it's pointing to the parent again. So as you can see, it's pointing up to its parent. Now we get to line 5 where we define a new scope. So we get to line 6 here. There's going to be a new variable y, and at line 7 it's going to go out of scope. So by the time you reach line 9, you have a new declaration of a variable w. Notice that this structure here pointing to its parent tells you which part is accessible at any given point. So when I'm in line 6 over here, I know that I'm accessing the symbol tables by looking at this one, which is the closest, and then going up to its parent and then up to its parent and so on. If I'm in line 9, then I know that I start from here, right? So if I'm looking for w, I'm going to look at the definition of w that's the most closely defined, which is namely the one defined here. If I want to look for z, I would go up to the parent to find the value of z. A slightly different data structure to store the same information that we saw before, just stored as a sort of a stack data structure. And so the symbol table is treated as a linked structure of scopes. Each scope stores a pointer to its parent, but not vice versa. And if you look at any point in the program, as we saw in the previous slide, the symbol table appears to be a stack, right? So it's very closely related to the previous method of doing it, except here explicitly we're storing all the different scopes in this kind of tree structure. And this data structure for the symbol table is called a spaghetti stack. It's not something we are going to be using in the homeworks in this class. In this case, the data is stored in heap memory rather than stored in stack. So when you have a recursive function, it's going to allocate more memory in the heap to keep track of all the local variables. And generally, it's useful for programming languages that support continuations. So if you've read up on the yield function in Python, for example, that's an example where you yield at a certain point in the program, you transfer control to a different function, and then it's essentially creating these iterators that need to keep track of the local variables in different functions. In order to do that in a stack, you would have to do a lot more to keep track of everything. And essentially a spaghetti stack is very useful when you want to deal with continuation. So in programming languages like Scheme or Standard ML, you would implement the symbol table using a spaghetti stack to support first-class continuations. So you can always implement continuations by doing something else and just using a stack-based symbol table, but it's not considered a first-class support for continuations in that case. Let's look at inheritance. So here's a sort of Java-like programming language. So there is some class which is a base class, and it has two variables. It has a private variable, a protected variable called baseInt, and a public variable called public baseInt. And let's say that you're in the root scope, then we create this new class called base, which is underneath the root scope, and it has these two variables defined, public baseInt and baseInt. Now there's another class which is extending the base class, and it has its own local variables, derived int and public baseInt, and it has a function. So this derived creates these two local variables, and then it has a function called do something. So this function is something we can trace and see what's going on with scoping when you have inheritance. And so this example will show us what we need. When I go into do something and I go through these print statements, The first print statement is printing public base int. So when I want to print public base int, I know that I've redefined it over here and its value is 4. So it's going to print 4 because the closest thing it has is this in the symbol table. Notice that now, don't be confused by the fact that I'm keeping, in this case, in the symbol table, I'm actually keeping the values. I'm not keeping the line numbers because I don't care about that in this example. I care about the values because I'm printing them out. The next line, I print base int. Now, if I look at base int, it is protected variable, but it's part of its derived class is extending base, so it gets access to base int as a result. And the value is 2, so it prints out 2. The next line, it prints out derived int. Derived int is defined over here, right? So the derived int, the value is 3, so it prints out 3. In this case, we see where the information is flowing. It's flowing both using scope and using inheritance. So let's look at a new variable that's defined here called public base int, which is shadowing this definition over here. So when I look at this print statement where I'm printing public base int, it's going to look at the closest definition, which was just from the previous line, and it prints out 6, as you can see here. So you can see that scoping interacts with inheritance in some subtle ways, right? Okay, let's take another example. The scope of the derived class has to store a link to the scope of its base class and then look up the field of the class in the scope chain until you find something and you can use it, or if you don't find something, then semantic errors is raised. In object-oriented programming languages, you often have variables that let you do explicit disambiguation of whether you're doing scope or inheritance. And these variables are called, they're different programming languages call them different things, but they often call this dot something or super dot something. So let's look at an example here. There's a base class with the value 1. There's a derived class with the redefined values 2. And then inside this function do something, there's another value 3. So when you print this over here, the first thing it prints, if you print out value, is 3, because that's a definition that's in local scope. If you try to print this dot value, it's using the method in the object, the variable that's defined in the object. So it would print 2 because it's explicitly using the class variable. And if I want to use super dot value, it's going to look at base, and inside base, it's going to look at the variable value and print out 1. So as you can see, these explicit disambiguation of inheritance versus scoping can be done in object-oriented programming languages. If I remove this local value here, this value is still going to print 3. This dot value, though, it doesn't have a local one, so it's going to look for whether in the class that it's inheriting from, there is a definition of value. So it's going to print 1, which is the same as super dot value, right? So it's going to print 3, 1, 1 in this case. So when you want to disambiguate these scopes, you want to maintain this sort of second table of pointers into the scope stack. And when you're looking up a value, you begin the search from that scope, right? So you're chasing these pointers from the most local symbol table up to the most general one. And some languages allow you to jump to any arbitrary base class. For example, C++ lets you define where you want to get the variables from. And so the compiler has to deal with this kind of situation in inheritance. So there are single and multi-pass compilers. So when we're doing parsing, we're always scanning the input from left to right. And since we only need one token of look ahead, we can do lexical analysis and parsing simultaneously in one pass over the file. And some compilers can combine lexical analysis, parsing, semantic analysis, and code generation into one pass. Essentially, we finish parsing, we have done all the semantic analysis and code generation. When you're done at the end, you've scanned your last token and done a bunch of reduce actions. The end result is you get the output code generated. So these are called single pass compilers. There are other compilers that rescan the parse output, or the abstract syntax tree at least, which is the output of the parser, multiple times. So they might traverse the abstract syntax tree multiple times in order to do code generation. And these are called multipass compilers. So some programming languages are defined in such a way that they support single pass compilers like C and C++. Certain aspects of its semantics are simplified so that you can do it in a single pass. Some languages require multiple passes because it's not so easy to come up with all of the semantic or find all the semantic errors without doing multiple passes. And Java is an example of that. So many modern compilers use multiple passes over the input program. We are going to do a sort of hybrid where we are going to build the AST, but then each time once we build the AST, it's going to do code generation by traversing the AST and doing code generation and semantic analysis at that point. If you handle scoping in multipass compilers, the first pass is usually parsing the input into an abstract syntax tree. The second pass, you walk the AST gathering information about everything in classes. So we kind of do a little bit of that when we look for backward or forward function calls, for example, in decaf. We have to make sure we gather all the function signatures. And if I'm going to generate a method call to a function that's going to be defined in the future, I need 2 passes. Or at least that's an easy way to do it for decaf, at least. And then the third pass is to walk the AST, check semantic properties, and do code generation. So our approach in homework 3 and 4 is a little bit of a hybrid. It is generating the AST incrementally while parsing. It's also doing some semantic analysis while it's doing the parsing by storing stuff in the symbol table. And then traversing the AST, there are some aspects of multiple passes when we deal with forward function declarations. So in summary, a semantic analysis verifies that a syntactically well-formed program is additionally passing all the semantic tests that we need. And that will help us when we do code generation. So we don't end up generating code for something that's semantically incoherent. And scope checking determines what objects, classes, functions, variables are referred to by each name in the program. And the scope checking is done using a symbol table. There's various issues with scoping in inheritance in object-oriented programming languages. And sometimes you need to do multiple passes in order to gain information to find all the semantic errors in the program. And in dynamic scoping, the actual execution of a program determines what this name refers to. There are some programming languages where the variable names that are in scope can dynamically change. So a language like Perl has dynamic scoping. I don't cover it in this lecture because it's already way too long. There are some extra slides that talk about how dynamic scoping works in a programming language like Perl. We haven't really talked about multiple inheritance either, but it's more of the same as what we discussed. We need to search in multiple paths rather than in one strictly linear path. So it's fairly similar to what we've talked about already, but slightly more complex searching needs to be done in the case of multiple inheritance.